So welcome to the, I think, third lecture on foundations of dynamical field theory, and this one will emphasize memory. I again remind you of what we did last week. We discussed selection in some detail. I pointed out how if you have multiple inputs, like in this case for saccadic eye movement, two visual targets, how the field can account for the fact that visual saccades tend to select one of those targets. Really comes down to the bistable nature of peak generation. If you have global inhibition, so peak could be positioned over the local maximum of one input or over the local maximum of another input. And these two states would both be possible stable states, and which one you realize will depend on initial condition. And often that essentially comes down to which of the inputs arises a little earlier or is stronger, and therefore drives activation up to threshold faster. And then the transition to averaging, where these two peaks would merge in a single peak, is sort of one of the features that the field explains, sort of makes obvious that the selection is not a trivial property. And then we discussed in some detail that most ways that selection decisions are studied are in the reaction time paradigm in the widest sense. That is, there is a particular signal that tells you what to do and or what to select, and then to also do that selection, and you're measuring how long it takes to then respond appropriately. And this imperative signal is interpreted relative to the task that there is some knowledge that you have about what possible choices are. So in classical paradigms, often by instruction, sometimes by perceptual layout or by memory. That's why I'm mentioning that, because we'll now get to the memory part. So I talked about the two roles of Preshape. The Preshape is the structure in the field before that imperative signal arises. And here's the image, the case where it's just a weak influence. So the Preshape is a small input to this field compared to the specific input that represents the imperative signal. And therefore, the decision what to realize, what solution, which peak arises, is largely specified by that specific input. So it's the system selects in some sense, but it's actually a unique response that arises. And I pointed out in the lecture that there's still some subtle influences of these, of the Preshape, of this pre-activation of certain choices. We looked at metric effects and the classical effects like the Hick-Hyman law and so on. So you can think of these as small biases in the system that make some choices easier and thus faster than other choices. While the more qualitative regime is when that pre-shaping is dominant, is large compared to the specific input. You can still get peaks being formed by boosting the entire field, so not providing specific information about which choice, but just saying, go, do a choice. And that leads then to categorical responding. There's all the different outcomes are pretty much magically identical when you give these different inputs. And then we discussed how that gives rise to a couple of effects. So that's the role of Preshape. And we even looked at this paradigm where we can see the pre-shaping of the field, because we manipulate how long into the preparation process we're actually observing the response. We impose a particular stimulus response time interval by providing the imperative stimulus a certain amount of time before the go signal. And the go signal, by being part of a periodic pattern that a metronome provides you, can be actually imposed on participants. But participants can learn to move, for instance, on the fourth tone. And I showed you examples of pre-activation, guessing that we have very short time to prepare the movement. You have a default response, and that then evolves continuously in time as you have more time to prepare to the correct response. And I did that also for these movement parameters. It's actually some work that I skipped, where it is actually possible to directly observe that pre-shaping at a neural level. This is in the slides that have been sitting on the webpage for a couple of weeks now. It has to do with, this is from the motor system with neural representations of movement parameters such as movement direction. So a monkey who makes a center out task, let's say 6 targets possible here, like from the center to 6 tasks, you will record from neurons, for instance, in motor cortex or in premotor cortex. I showed one slide of such recordings earlier. And then you find that the firing, these little dots are spikes that are recorded in different trials. Every line is a trial ordered by reaction time. You find that these neurons fire more for some directions than for other directions. So they primarily fire actually before the movement starts. Here, this row of dots, these markers, is when the movement starts. So most of the firing here is in the preparatory period. And you can use these tuning curves to move in direction. Here is schematically shown by these green lines to construct something we call a distribution of population activation. Simply, every neuron votes for its tuning curve with its current firing rate. Mathematically, it's sort of like a projection onto a space, the space of functions of movement direction. So, for instance, here these neurons whose tuning curve is maximal here around this movement will fire a lot in that condition, and therefore their tuning curve is multiplied with a large factor, while the neurons that are centered somewhere else are multiplied with less. And if you superpose all these curves, you get the red curve that is centered on the current choice. That mean of that distribution is called the population vector. Some of you might have heard that. And by using time slices of firing rate in different time slices, you can actually observe the temporal evolution of the neural representation of movement direction. This is an example like that for many neurons. And there you see there that at the time when the peak arises, a peak already arises a little bit here that's centered on the movement direction that is coming up, and then toward the response signal, the peak actually really rises and becomes macroscopic. Here are different conditions, there's a different way of doing this. Here is what I just showed with less smoothing. And here is a case where 2 targets or 3 targets are pre-cued. And this always looks at the local maximum in the field at different moments in time. You will see that when you have 3 targets, the maximum sits over the center of these 3 targets. These are the 3 targets that are cued in different cases. When you have 2 targets, it sits on the center of these 2 targets. And when you have cue a single target, it sits right where it's supposed to sit. So you see it reflects the prior information about what target comes up. So that's a direct neural representation. I'll skip these slides. So we call that pre-shape and pre-structuring relative to that moment in time when you are giving the signal and the system an imperative signal, so that now it generates a response, it computes it. Classic information theoretical approaches suggest computes the answer. And that computation is less time consuming when you have already a lot of pre-structuring of the representation that matches what you ultimately have to respond, and less so if it doesn't match. And the exercise that's due tonight is actually probed that aspect. Now, in these experiments, there are we were saying pre-shape and pre-structuring, but just because it's before that moment in time, but there might be different ways of how that comes about. So some examples I was suggesting, it's really just the perceptual layout of the world. If you're, let's say, grasping an object and there are only a handful of objects on the table, then you might naturally assume it's going to be one of those objects, and you might prepare movements to those objects. In other cases, it's really by instruction, where you tell people ahead of time what the different possible stimuli are or different responses they might have to generate are, and so on. And in other cases, it's really from experience. So, for instance, if you have to press buttons on a table, and I don't know, there are 8 buttons, but after some time you find that only 4 of them ever light up, and you ever have to move to them, then over time, as a participant, you accelerate and become quite good at selecting one of those 4 choices. So you're learning from experience what the actual number of choices are. That will be quite relevant to a lot of cognitive tasks. A lot of human factors work, for instance, is about things like that. The monkeys I was hinting at, of course, also do that this way. You don't really instruct these monkeys, you train them, rewarding them selectively for moving at the right time, and then removing to the button that was cued, and maybe taking into account the pre-cued information and not moving to the wrong button. And so they do this based on memory, and I will talk about memory now, how memory comes about. Now, there are two forms of memory that I will be talking about. One we refer to as the memory trace, and it's a sort of a model of longer-term memory, and I'll briefly mention that. And that's related to the kind of learning that many of you might be familiar with from neural network modeling. Memory is actually a really difficult topic. It's a topic of a lot of current research. The neural grounding of memory is actually not very well understood. It might be a bit surprising if you think of neural network models as somehow modeling the acquisition of memory, but it's not. It's actually the acquisition. A lot of the neural network modeling is actually the acquisition of, in a sense, of skill, of concepts, of categories. And we don't actually know if, or we have even some reasons to suspect that a lot of the mechanisms that are postulated there are not really the ones that are at work when humans learn concepts, skills, categories, and so on. And these models are not very good at explaining how from a single experience you form a memory that you then can reactivate under certain circumstances. And that's a topic of a lot of current research, often involving mappings onto hippocampus and different processes that would be engaged in this endeavor. Now, if you look back into the literature, the simplest and historically oldest forms of learning that people were looking for seem much simpler. And William James famously opens his book on psychology on habit, on forming habit. In the meantime, nowadays we have a much more refined view of what habit formation actually is. But very generally, there's sort of an idea that a very simple form of memory would be that something that you just did or just experienced perceptually is easier to experience again, or to do again, to see again, or to act on again. It's the opposite of what is called habituation, which is that what you just did or just saw is harder to do again. So that will be essentially inhibition building up, while habit formation would be excitation building up. So it's very low level, simple kind of memory. And there are actually signatures of that kind of behavior in animals. For instance, habituation is very often said in animals that in terms of needing a stronger stimulus to elicit the same response again after a certain number of times of having experienced the response, a stimulus. And habit formation is often observed as a form of familiarity preference, that is, that you react more easily with less stimulus to something you just experienced. So these two are opposites, and actually it seems like both happen, that you tend to early on have a habit kind of reaction, that is familiarity preference, do the same thing again, and then after more experience you tend to then inhibit that behavior and tend to show habituation. So in dynamic field theory, we have a simple mechanism of how we account for such effects. We call that the memory trace, and that connects to an old concept in psychology, the memory trace, which wasn't very well grounded neurally, and our memory trace is also not very well grounded neurally. There are a lot of candidate processes like that, but it is not as well understood as activation dynamics itself. It's, for instance, not clearly mapped onto the modification of synaptic strength, unlike Hebbian learning. And I'll sketch this. It's really a phenomenological theory, and I'll point to how it relates to neural networks. So let me first just state what it is. And so if you have a field like this here, activation over a feature space evolving in time, and here this would be a suprathreshold peak, that this being above zero and suppressing the neighbors, and under such conditions we would postulate that there is a field that we call the memory trace. It's not a neurodynamic field, it's a different equation, it's very simple linear dynamics, that would slower than the activation in this field, build some form of activation or memory trace at the location in the field at which a suprathreshold peak is currently present. So the buildup here would be the buildup of a memory trace at that location. And that memory trace would conversely act in an excitatory fashion back onto the field and create the pre-shape, create that pre-activation or base activation. Might not be by itself enough to sustain a peak, but it will be a bias input to the top field. If this is an inhibitory connection, then that will be an account for habituation inhibitor memory trace. Here's an excitatory memory trace. So mathematically, it would be really that in a field equation of this generic form, you have another term from the memory trace that here is excitatory, could be inhibitor in other cases. And the memory trace is defined over all the states X of your field, the dimension along the dimension. Evolves in time like a dynamic system. It has a minus u term, which means together with this parameter that it has a particular time scale on which it evolves. And it receives input from this field. So the u over all x prime, sigmoid, so all the suprathreshold activation induces a peak. This will be typically some positive Gaussian kernel. So there could be a little bit of a spread that you don't excite only the exact same location x prime at which there's a peak here, but maybe also the neighbors a little bit. So this would be a Gaussian kernel. That's an empirical question of whether the memories tend to be smeared out a little bit. That's often a good model. You're also, also activating neighboring sites to the site you're just looking at. So that's the mathematical model of a memory trace. So you see this here is not a real neurodynamics. It's not an activation dynamics. You could think of this as a synaptic process, but it's not really formulated as a Hebbian learning rule. I did not put that slide in. This is formulated more like a bias term. You might know that in neural networks, there is a term that contributes to every neuron's activation that is not driven by input. Also, there's the input-driven, like synaptic connections in Hebbian learning would be somehow modulating this input from the outside, strengthening those inputs that are successful in inducing peaks and weakening those that are not. And this is not like that because this is just an additive input that's independent of the stimulus. So it will be just predisposing the field to make peaks at the same kind of location, independent of how that peak comes about, whether it's by input or by boost or whatever. And so there will be a bias term in the classical theory. And the bias term is important for some, like in deep learning, it does play a role, but in many cases, it's not very important because it's just one input or one factor, and there are many other connections that play a role. So it's often negligible. Well, you will see in a moment that, and you know already that the amplification of small inhomogeneities in the field makes that such an input can actually make an important difference. And that's one of the themes. The actual mathematics we use are a little bit more involved. We, for instance, we postulate that the memory trace is invariant when there is no suprathreshold activation. So there is no place in the field where this here is above zero. Now then this whole term would be zero, and according to this equation, then the memory trace would just decay to zero. So you would be forgetting whatever you built up. That's not empirically observed. We find that when there is a familiarity preference, for instance, that can be still observed after a long break in which there was no stimulation or no action plan. So we're assuming that the whole right-hand side is zero, multiplied with zero, let's say, in a gating way, when the field is not active, so that you can store, in a sense, the memory trace. Another technicality is that in many cases, there's some evidence for the growth of a memory trace, or how quickly you get into this familiarity preference kind of mode is faster than the decay. Decay would still occur here if there is some location in the field where there's suprathreshold activation. So for some x, close to some x, there would be x primes that drive the field and that would drive the memory trace to build up around those locations. Then any other location at which you are looking would have a decay, because at those other locations, x, where there's no nearby activated field states, this term would be zero and you would have a decay. And so these two processes are empirically often found, empirically not in behavioral experiments, Berkeley found to have different time scales. So for instance, you can have some interference when there's another, when you learn one choice, another choice is now being present. But it takes longer to get rid of a bias that way than it takes to first build up a bias. So here's an illustration of what that mathematically does. So here's an activation field, and there's some peaks induced by some inputs. Initially here on the left and then here on the right, you see there are boosts here that bring up the peak. There's a peak here, the boost brings that up, and then there is some activation here at the other side because there's input, but the selection decision made that we only get the peak here on the left. And similar here, there's also some input here, but the peak on the right wins. And so this illustrates that what you lay down is a memory trace at the locations where there is suprathreshold activation. So here, this suprathreshold peak drives the memory trace, and the memory trace conversely drives this peak. There's a ridge essentially here that makes this the more pre-activated choice. While the input that you have at this location that's not successful in inducing suprathreshold activation does not leave a memory trace. Only when later you actually select the rightmost location, then a memory trace is being built. And you see here this forgetting. There is, for instance, this interval here in the middle, which is this plateau, there is no forgetting. See, the memory trace is just constant. That's because there's no peak anywhere in the field, and then the equation just shuts off. But then when you induce a peak here at this location, memory trace grows here. At that time, it decays here. So there is, in that sense, competitive decay. This was used many years ago, for instance, to account for how probabilities are represented. Remember, I told you the experiments that account for the modeling of the Hyman effect, where we say, well, a more probable choice has more pre-shaping or pre-activation than a less probable choice. How does that come about? It can come about by a memory trace through the mechanism I'm hinting at here. So if one location is activated more frequently, there will be more times when it memory trace rises than when it falls, and the inverse for the other location. And the combination of those two can actually lead to the memory trace essentially reflecting the frequency of a choice, or how much % of the time did that choice actually arise. There's an issue of, is it time or is it number of times? And that has to do with trends and so on. So it's a bit more complicated than that. But roughly speaking, this is a model of how probabilities can be represented in the amplitude of the memory trace. In the end of this lecture, I will show you an example of that, of how the memory trace can be used to account for some results. Now, I don't want to go too deep into that because I first want to talk really about working memory. So working memory, remember, is the other kind of, now memory is the influence of the past, right, on the present. And the memory trace now is the influence of the past through a lot of time. And working memory is the influence of the just recent past. And remember, in the field, what we have is that there are conditions under which an input that induces a suprathreshold peak, it's taken away. Here in this frame at the bottom is taken away, but the peak might be sustained, persist. So then we say this is a working memory of that previous experience, of the fact that there was that peak. So working memory is sort of the idea. It is something that you can work with, that other representations in the system can work with. So for instance, if this is about space, then you can use that spatial information, for instance, to plan a reach or to do some inference about spatial representations. So it's an activation that can have the same effect as activations that are supported by perception input. So working memory really means activation. So it's sort of like a perceptual activation, but you don't need a stimulus for it. We're, of course, aware that usually working memory of perceptual events don't have the same phenomenal quality as the perceptual events. So you're not hallucinating a bottle if you remember where the bottle stood or which color it had, but you can retain that information that you acquired from perception about the bottle and then respond about questions, 2 questions about that quality, for instance. supposedly based on these sort of ideas. And in the lectures, we pointed out that this is a feature that's a feature of that emerges from the fields under appropriate conditions. So for instance, here the resting level is a little bit lower, and under those conditions, when you remove the input, there is no peak. No peak remains stable. So you see the subthreshold trajectory is just a little lower, at a little lower resting level than here on the left, and it does not, this field does not have a sustained peak. So that's what we know. And now this is, as you know, empirically, you know, some support for this idea from neural data and so on, and it's a complicated literature. One interesting aspect that I wanted to point out here is that the very nature of the notion of a sustained pattern of sustained activation, that it's not actually strictly speaking stable. And what's not stable about it is that this peak here, if you were to shift that peak along the dimension, that will be just as well a stable state. There's no restoring force. You're not going to, yeah, if you shift this, let's say, to the right, there's nothing that pushes this to the left. Now, in the presence of input, there would be, you would be climbing here that hill, because the left side of the peak gets more input than the right side, and then the peak would grow on one side, and the inhibitor interaction would make it decay on the other side. So it move until it is positioned on that local maximum. You experience that in exercise 3, I believe, or I don't know, or was it 2? In one of these exercises, you actually played with that, moved the peak around by moving the input. So if you do that experiment concretely, or as a thought experiment on this mode here, then you will not see that. If you somehow shift the field to a new location, it just stays there. And if you were to add noise to the field that's sufficiently large, then you could get that peak actually drifts. For instance, if by fluctuation you have a little bit more activation on the right than on the left, then the next moment in time when that fluctuating input goes away, then the activation on the left could suppress the activation on the right, could suppress the activation on the left by inhibitory coupling, and the peak would permanently remain shifted. So this would lead to some drift that could be random, so induce increasing variance over time. It could be systematic if there is some inhomogeneity, if there's a little bit of a tendency to move to the right, to the left in general. And that actually turns out to be empirically real. It's one of the experimental signatures of this mechanism for memory. So here's work that my colleague John Spencer did over a long period. He actually did his PhD thesis to test the Alhagen-Schöner model, and he devised these kind of experiments. And there's one, you know, historically speaking, funny aspect of that he first found the opposite of what we postulated. The memory trace would predict that you would tend to sort of go to places where you've been before, and he found the opposite in some sense. And later it turned out that that could be all sorted out, and both the predicted effect and a new effect are true. But that's not what I'm talking about here. I'm just talking about spatial working memory and drift in spatial working memory. So this was done partly with children, also with adults. The developmental aspect is also interesting, but I don't want to go too deep into that. And here the light is on in this room, and you see this girl pointing with a finger at a location, and that's the answer the participants give to the question, where was, for the kid, it was a spaceship that we showed on that screen. So it's been more precise. You have a reference point. This is where your finger is positioned initially, and then in some location, a target appears, and for instance, here for 2 seconds, and then there is a delay imposed, and that delay is being varied, and then you're asked to point to where that target was. So for the kids, you have a particular way, it's like ready, set, go. You control this way when they give the response. And for instance, in some of these experiments, kids had a little object that they would be placing on the screen, and this would be like the rocket that shoots down the enemy spaceship or something, just to make it more intuitive. But generally, you're just moving your finger or a cursor on a computer screen to the location at which you remember that object had to have been earlier. And when you do that, you find a couple of systematic effects. So here's some survey over different conditions. This is from there's a whole bunch of experiments done this way, and I'm just highlighting some points. So in this particular experiment, there were always only 3 possible locations at which targets would appear. They always included the center position, and then you could have plus 20 or minus 20 degrees from that position, always viewed from the start point. 40 or minus 40 in different conditions, 60 or minus 60, and 80 or minus 80. We looked at asymmetry, we looked at different probabilities that one occurs more often than other. We also looked at cases where everything is off the midline here to the right or to the left. All of these experiments have been explained by the model, but I'm just highlighting a few things here. So you see here two effects. This is the experiment, the right is the model. And on the top, you see systematic drift. So this shows up as the so-called mean constant error. That is, you're looking where participants are pointing relative to where the target actually was in absolute terms. So no cancellation of the sign. And it's always plotted in a way that you're saying when you go here, have a positive number, that means you're going away from the direction to the target. So you're outside, like if you have 20, then you're outside of the 20. And if it goes negative, then you're inside of the 20 toward midline, and mapping the left onto the right and so on. And so you see that across time, for most of these conditions, there is a drift away from the center. So drifting out, systematic drifting out, systematic in the sense, if you impose different delays, the longer the delay you impose, the more your mean has drifted out. The only condition where there is something different is the center condition, where you stay put. There's a little bit of a drift inwards, which can be theoretically understood, but certainly less than the drifting out. And it depends a little bit on how far the targets are away. Actually, the 20-degree condition, this one, is where there is most of the drift out. And the 80-degree condition, this one is where there is least. So when you're out here, you're pushed back least. So it looks like you have to be close to the other conditions, and it turns out you have to be close to midline in order to be repelled. So that's a systematic drift upward memory. So you're not precise, you're actually being really pushed out. This is in angle from the center. So 20 degrees is this amount, and you see that the maximum drift is up to about 7-8 degrees. This is a mean across participants. So it's sort of like this much, right? It's not quite half of this distance. It's actually a sizable effect. No, it's not a microscopic effect. The other signature that you see here is the variance from trial to trial. So how reproducible is that behavior? And you see that variance grows across trial. So if you respond immediately, you have very low variance. If you wait longer, then there will be more variance from trial to trial. So that's sort of consistent with the signature of the random walks. You went through the Einstein argument somewhere, where you thought through the fact that independent kicks, the system gets different points of time, lead to increasing variance across time. And so that will be consistent with that kind of picture. So we can model this from the kind of model that you're familiar with. And that comes from the fact that the peaks in the model that you're familiar with are not stable when they are in the sustained mode. When there's no localized input, they are actually marginally stable. That is, they are stable in their shape, but there's one direction in which they would be mathematically stable, but not asymptotically stable. That is, if you shift them, they stay close, but they don't converge back. This whole experiment was arranged to make the system as homogeneous as possible, in the sense participants were making these movements in the dark. All this surrounding stuff was not supposed to be visible to them, it was dark. We put this black cloth here also to make sure they don't see the edge of the table. There was, however, some position relative to this start button that was reproducible. You can see this little cutout in the table, and people were, of course, aware where they were there. And we've found in hindsight that that defines some kind of axis. So the system isn't actually totally homogeneous. There's some kind of midline axis that is perceivable and memorable. We did bring in markers sometimes to illustrate to the participant what the array is. Here's an example. You see there's a little marker here that is lined up with that initial position, and that defines some kind of axis. And if you do that, then you get very pronounced effects of repulsion from that axis. And in fact, you can also shift that axis around, for instance, by shifting everything here to the right, and then you find actual repulsion around that imaginary axis. So you can impose, in some sense, some spatial reference relative to which this drift occurs. So here's an account for that. The midline is here represented explicitly by a peak in the field. And here is a peak induced by the current stimulus. This is a case where we take into account that the fact that excitation and inhibition are not in the same field. So this is the inhibitory interneuron population, and this is a working memory. So we have two fields: the perceptual field directly that reflects the current input, and this is the working memory field. So here you see the peak decays when the input is removed, and then remains actually here as a trough. Well, this is the work memory, which is induced by this peak, but then when the input there is removed, activation stays and sustained. See, there's also some subthreshold activation here at the midline, at that perceptual marker. And the repulsion that you see here, see this drifting out, that ultimately comes from inhibition. It comes from the fact that this activation here spreads inhibition. So it pushes this peak out by eating away here on the right end, and then field builds up activation on the left end and effectively drifts out. And this is the model that accounted for the effects I just showed, that made this kind of data. So this is to say that there are some signatures of this being a model that actually captures behavior signatures of working memory. We have a lot more. We have looked at metric effects of various kinds, and I'll now elaborate at least one of those predictions, I believe. But it takes me a little extra step to first really think about how we actually make measurements on working memory. I'll get to that in a moment. This is based on change detection. We'll actually actively model that. So let's just take that for granted for a moment and say we have some way of measuring working memory that's expressed here by percent correct. So it's percent correct really with respect to people having to answer questions like, was this what you saw or was it that? So you show them something, they memorize it, and then you remove it, show them something else, and have to say, is this the same as what you saw previously or not? And then you can test whether they have a good working memory of what they just saw, but you also actually have to say it depends also on them being able to match what they currently see to the past. There's a question here, if there's no drift when there is nothing suggesting a midline. No, so that's a good question. And it's a very subtle one. We struggled with that for a very long time. So we can say that by perceptual markers, we can shift where the drift occurs. So it is tied to perceptual input, and we can also make it more or less strong. So if we get very strong perceptual bias markers, then we can make a stronger drift. But it is difficult, if not impossible, to totally get rid of that effect. And so that's what led us to postulate that there will be always some kind of implicit midline, that when you set up with your body somewhere, you close your eyes, very easy for me right now, close your eyes and sort of try to be neutral, that there is some body configuration that says here is a imaginary symmetry line that I anchor my body perception to, and you will see repulsion around that line. That's what we know, and it seems to be always there. It's kind of interesting because the outer world always seems to be there, right? And even if you close your eyes, you have a sense there's an outer world there, and it is anchored in space in the sense it doesn't move with your head. You can move your head around, you still think there's the world out there. It doesn't depend on having eyes open, eyes closed, and even if you're moving with reaching to objects, doesn't depend on where your hand position is. Now, it might be possible to shift that around. For instance, if you set yourself up like that, and it is also anchored to an object when you do that, and then you shift yourself relative to that object, the imagined boundary can remain stuck to that object. And we have had one experiment where we actually really probed that. There's some evidence from Hollingworth, someone called Hollingworth's lab, who asked people to look at an array and pay attention to a particular item, and then they represented the array, either the whole array shifted or shifted relative to that item, or different items being shifted in different directions. There's a German psychologist who has a whole paradigm where she manipulates how many of the items, which percentage of the scene is being shifted. And in cases like that, you find that you can attach yourself to that frame, and if there's perceptual cues to that frame, then the frame moves with those cues. And the more items are consistent with that, the stronger the corresponding effect. But you can also remove all those cues and still have a midline. That's very subtle. Interesting. Oh, that answers that question. Now, so I'll get into how we actually measure the working memory in a moment. I'll answer your second question. So, is there also a study showing that we have a pull to the right, for example, when we walk with our eyes closed? Maybe that's somehow related. So you mean like an asymmetry? I'm not sure that bias is related, but certainly when we are, let's put it this way, when we are in a marginal stable state like this, we don't have perceptual information about how we're anchored in the world. Then we are subject to drift. And that drift can be random. I already hinted that there will be increase of variance over time. But if there's any inhomogeneity in the system, for instance, you have a slight left-right bias, then that will be an opportunity for that small effect being amplified, because it's not resisted by stability. So then if you leave enough time, there will be drift in that direction. So it's easy to think of, for instance, asymmetries as expressing themselves when you remove the anchoring. As long as you have anchoring, you open your eyes, you see some perceptual structure. That's a very, very minor asymmetry, so it doesn't really matter. But if you remove all these anchors, and anchors concretely means localized inputs that your peaks can lock onto, then you will be seeing these biases. So good. So let's go back to the to this working memory issue. So one thing I want to get out here right away is these working memories have limited capacity. That's a very famous fact. There was some historical evolution about what that capacity actually is. And now the magic number is more likely to be 4 than 7. There's a slight difference between phonological memory, so speech or sounds of speech, versus visual working memory, but those can be understood. And overall, the idea is it's a small number. It's probably 4, maybe 5, something around that. It's very limited. And it is limited in capacity with respect to objects. And by objects, we mean stuff that is localized in some sense, localized in some space. It can be really concretely here, visual space. So it's not about how many different items of information you have to keep in memory. So here, for instance, you see these objects have colors, and they have shapes, and like long and short, and they have orientation. And these kind of objects, you see, they have 2 colors, and inner and outer. And using things like that, you can make every item have a number of features, 4 or 5 features that you have to remember. And so if you think of it that way, then a display like that would contain maybe 8 items of information, because you would have to remember the 2 colors at every location, or here even more, because you would have to remember the location, the orientation, the color, and the size of the object, stuff like that. And it turns out that the capacity is not a question of the number of pieces of information that you have to store that way, but on the number of objects. And so that really means on the number of locations, because we talk about visual objects, just something that is localized somewhere. And that's the summary of all this work. Clark and Fogel, with whom we actually worked in the concept, I'll show that in a moment. They showed that if you look at forgetting, so deviation from perfect remembering, decays you're off, and you can see that at 4 is where it starts to get bad, and you see the different combinations where the number of items, the number of pieces of information you have to store varies, but the number of objects is always as dictated here on the horizontal axis, then they all lie on top of each other. So it's really the number of objects that matters, not the number of individual pieces of information. That's interesting for the theory. I will explain that aspect of the theory in the new year. It's a very advanced topic that has to do with binding through space that we might not be able to understand very closely. Here, just want to make you aware that there is this capacity limit, and the capacity limit is very natural. In the fields already hinted at that in earlier simulations. So ultimately has to do with the fact that as you're adding peaks, they inhibit each other, the peaks. And so at some point, we are not able to add a new peak. But of course, the number 4 especially can make models, DFT models, where that number is pretty much almost any number that you can think of, just by tuning the parameters to have less or more inhibition compared to how far you are from detection. That is consistent with all of that being mediated by something that's localized, because it's the number of localized pieces of activation that matters. So capacity limits are natural, and they are natural in DFT, so that's the good thing. The number 4 is interesting. There is, I talked briefly about saccadic eye movements, and we generally think of selection decisions being made all the time at all levels, and leading to some form of attentional bottleneck that you're only paying to one or a small number of objects at any time. And in that respect, the number 4 might have to do just with where you're coming from, where you're going to, plus a little bit. So you might always just store the recent history and just enough to decide the next, maybe the next step of attending. Everything else is not in activation memory. Everything else is already learning, changing synaptic connections. Okay. Just said that. Now, there's actually, go skip that. There's very interesting work on the spatial precision hypothesis, which I didn't explain this time around. A former student of John Spencer did a very nice review on that, and she found that the capacity evolves with developmental age. So adults are around 4 and 5, and then younger children are much lower, like 3-year-olds, capacity around 2. And we can predict these she can predict these kind of curves from experiments that measure how precise spatially kids are, and how much drift there is actually, and the drift reflects capacity, and that's a prediction of the field model, and that's powerful for us. But this leads a bit too far. I don't want to go too deep into that. Instead, I want to talk briefly about how we measure working memory and what the underlying processes is, and that actually then, for instance, reflects that the actual number of peaks might be a little bit higher than the capacity that you measure, because in the measurement process, there are multiple ways how you can make mistakes. But I will not go into all details. So the standard procedure in many of these cases is that you have a temporally structured sequence of events. You are presented with some items here in visual working memory, and then you delete these. You have some time to look at them. You delete them. This is the delay that you impose. That couldn't vary. And then you show participants a new array, the test array, and they have to say whether it's the same or it's different. Here, for instance, you could say it's different because this item doesn't match, but remember, you only see this, previously having seen that. There are versions where you have to actually point out which of these is different, and various other things, or you have to point at them. But let's say first approximation is just that, just saying it's same or different. And so that means that there is some difference between the representation in memory and the representation that you have perceptually, because you're able to make that comparison, right? So you have to have different substrate for that. And we came up with a model for that many years ago, which turns out to be connected to a very interesting literature on the canonical cortical circuit. Again, I wasn't going to go too deep into that analogy. Let me just explain the idea, and then I'll show you some simulations. The idea is that there would be a separate perceptual representation, as a neural representation for the percept versus for the working memory. Now, that's what I just said is necessary, and we're just postulating that. So that's trivial in a sense. But what we're postulating here specifically is that there is in some way the associated inhibition that you always need, right, to get anything stable. You have to have that inhibitory contribution, that is shared. That is, there's an excitatory level for perception, there's an excitatory level for memory, and there's an inhibitory layer that is driven by the perceptual layer, but also driven by the memory layer, but that conversely inhibits both the perceptual layer and the inhibitory layer. That's where you talk about a 3-layer model. So one inhibitory layer in the middle, and then 2 excitatory layers, a perceptual one and the memory, working memory one. So the perceptual one would be the one that leads phenomenally. If you have a peak there, you're seeing that thing, while the working memory layer would be one where if you have a peak there, you know that there's this thing, but you're not necessarily perceiving it. You don't, if it's not present, then you're not going to hallucinate seeing that either. The perceptual layer receives direct input from the sensory surface, from the stimulus, while the memory layer only gets input from the perceptual layer. So anything that you perceive will drive the working memory. It's not directly that the sensory input drives the working memory. You could postulate that as well, but it works without that. Actually, there's something interesting about that. If you take our typical models and you make this all symmetrical, that is, the coupling from this excitatory field to the inhibitory field, and the reverse coupling here is the same strength, inhibition is the same strength, the fields have the same parameters, and the only difference is that this one gets input from the outside, while this one only gets the input from this field. Then generically, what I will just show you occurs, which is the change detection situation. I'll show you that in the simulator. Here are the equations, and I just showed them to tell you it's all the same sort of stuff. Right? Every field has a dynamics of, u is minus u plus resting limit plus input, and then these interactions have these various forms. So the intra-field excitatory interaction, CUU, this is a purely excitatory kernel, and then you have an influence from the inhibitory field V with a negative sign, and you have an input from the working memory field, which can be positive. This one I didn't mention. You can also drop that. In the inhibitory field, same structure, it doesn't get any direct sensory input. It gets driven from the U field and also from that memory field with the kernel. And the memory field, minus W plus resting limit, the same thing, doesn't get direct sensory input. Instead, it has this excitatory interaction within the field, and it gets inhibited by the inhibitory layer, and it gets driven by the excitatory layer. So when I previously said symmetrical, then all the connections between U and anything else are the same as the connections between W and anything else in the idealized form. In models, we don't always follow that symmetry, but that would be just the extreme limit case. And then you will see what I'll just show you emerges there. So notice the stimulus only goes into the excitatory perceptual layer. There is no self-excitation in the inhibitory layer, right? Inhibition can only do inhibition, so there can be no self-excitation of inhibition, and no stimulus input into the working memory layer. So I'll just simulate that. And there is in Cosivina, there is a module like that. It's called Launcher 3-Layer Field Canonical. So you can find that if you go to the dynamicfield.org webpage, go to Cosivina and find the corresponding code. This is not contained in the web-based simulator. It's a 3-layer system that you can load some parameter values. These are some interaction parameter values. So here you see, again, the excitatory layer, inhibitory layer, and that working memory layer. and the parameters are tuned correctly so that you will see now I can induce a peak here on the top in the usual way. And now we go through detection. And as we go through detection, there is a peak in the inhibitory layer and in the working memory layer induced. And you see under the conditions I have here, this is even enough to make the initial peak go away in this top layer. It's inhibited by that shared inhibition. And for me to get a new peak here, I would have to give a lot more input than I needed to get it in the first place. And that is how the system is change detector, because essentially when I provide an input that is not too different, I'm shifting, oops, it's too strong. I'm shifting this around a little bit. Then if I provide an input that is sufficiently different, I am able to induce a new peak. But if I'm providing input that is not different, then I'm not able to induce a new peak. The simulator that's available online has different parameter settings that we use to fit adult versus non-adult data. So I was just hinting that there's a whole theory that I didn't really elaborate on how these things develop. We have the spatial position hypothesis that essentially says that in many different kinds of paradigms, children have weaker interaction compared to input. They're more input driven. They have weaker interaction in the sense that the kernels are broader and the amplitude is less, so that overall there is less activation contributed by the kernels. At the end of today's lecture, I'm going to actually take you through one paradigm from which this kind of idea comes. And there are very different experimental settings where you can see signatures of such a developmental change from more input-driven to more interaction-dominated. We call that the spatial precision hypothesis out of some signatures. Some signature has to do with how precise you are in discriminating metric dimensions, and space is one of those, but you can also do that in color space or in orientation space. And so we have different parameter sets that reflect different points along that developmental gradient. For some projects, some people can model a model of an infant or young kid versus an adult kid. That's why I have these different parameter settings sitting here. But it doesn't matter for the current purposes. So this will be the generic situation of how you would represent something in working memory. So this is like a gate. You have a perception here, but then it goes into this working memory layer, and there would be these together form a sustained activation, right? This is the excitatory layer. This is the corresponding inhibitory layer, and that inhibition would prevent the system from building another peak. So there's a question: if is this here really the perceptual layer, or is it some change detection layer that's only active when you detect change? And that's the better interpretation. So there will be actually yet another system, another layer potentially that is just for the percept per se. Because when you see something, you're not, and you commit it to work memory, because very easily if you just see something, you can report some feature values of what you just saw. So you have it in working memory. But while you have it in working memory, you still can see what you see on the perceptual surface. So this is not actually reflective of the perceptual field, it's reflective of a change. And in the models that I will be showing in the new year, the more advanced models, you will see that we have 4 such systems, including a perceptual layer and a detection novelty layer, change detection layer. And again, there is actually some hints that cortical circuits have a structure that can be mapped onto that. The cortical structure is more complex, but there is something like that in those circuits. The interpretation of what it serves for is typically not this one. I wasn't going to go there, but we'll be interesting topic at some point. Yeah, I think maybe that's all I want to say right now about that. Yeah, so this accounts for change detection. I hope it's so clear enough. That is, if a peak is formed, working memory is formed, then you have to move away from that location enough to be able to induce a peak with the same input strength. That's how we call that change detection. And we still in these models have sort of another, like a response signal. So again, this is the caricature. This is the field, that's the change field, the perceptual field, and the inhibitor layer, working memory layer. This would be a case where there's a peak here, and because of that, there's an inhibitor peak here. And so here you need sufficient input to overcome that inhibition from the shared inhibition. And so we also model the fact that there is a response system, which is not really the motor response. It will be some kind of inner monitoring system where you're registering whether what you see is the same as what you saw before or is different. So a peak in this field will be driving that different system. You're perceiving that something is different. A peak in this field would drive the same system. It's also sustained. And the time difference between those makes that your default response, the same response, can be inhibited by a different response. So by default, you will say the same. But if you get a change signal, you will start to say different and delete the same response. And so with that, we accounted for quite a number of effects. And so here's the most dramatic effect, I would say, because it's sort of surprising perhaps initially. It's an effect in which we predicted and empirically tested that this mechanism of change detection would be more sensitive to metrically similar targets, which is sort of the opposite of what you think. So here, the original is in colors, and we have one in orientation in here because this comes from a black and white publication. We did it with texture patterns. So you have a set of 3 items, for instance, and these 2 items are metrically so more similar in texture, and in experiment was color, while this one would be more different. And so what the theory predicts is that you will be better to detect change in these close colors than in the far color. Counterintuitive, because you might think, well, these same colors are more confusable, so you might be less certain about them, and therefore you might be worse in detecting change for them, but the opposite is true. In the model, this prediction comes from the fact that the peaks of the close colors or close items are metrically close in whatever feature dimension is represented there. When they're metrically close, the inhibition associated with the 2 peaks overlap somewhat, and that makes that these peaks are close, more inhibitive, closer to threshold, to being forgotten, and therefore the inhibitory influence is weaker. And the difference is hard to see, but this is a little closer to resting level than this. This is deeper. And that makes that these are, in a sense, more fragile. So when you bring in a change signal, they can respond better. I'll show that to you in a moment here. So here's an example. You have these peaks in working memory for the 3 items that you put the 3 items into working memory here. These 3 items, just barely. And now you're presenting a test item, and this will be a test item that is one of the 2 close ones versus a test item that is around the nicely separated one. And so let's maybe start with this one. You see here, when you're using one that's very far, this is the memory peak that you have that inhibits the change layer this much, and you are able to induce a peak here only if you have shift this quite a bit or have much more amplitude to get another peak out of this. While if you are in the close item, then these 2 are no, I'm wrong. This is the same trial, yes, where you're getting a item that is exactly on one of those locations. So you get no response because same response because there's no peak induced here nor a peak induced there. But now in a different trial, we're looking at a difference trial, so an item that differs comes in at a third location, but close to the two similar ones, so metrically close to the closer ones, versus a test item that is different, that is close to the far item. So over here, inducing some activation far from the item. And you see here, the item that was moved quite a bit is not, this is the same distance as that distance, but it was not able to induce a difference peak. So the activation does not go above 0 here, because this is broadly inhibited there. This is a very stable peak, and that creates a lot of inhibition, and it's not able to, therefore, to be overcome by this input. While around this location, the same input, same distance, now induces suprathreshold peak. And that's because these two are inhibiting each other, and therefore their inhibitory effect on this layer is less. You see, this is less deeply inhibited than around this, because these two are weakening each other and therefore cannot make as much inhibition on this system. So in other words, again, the two closer items create less inhibition than two far items. And here's the experiment that confirms that. So the experiments had color as the feature or orientation, and there are different variants of the experiment. It doesn't really matter. So when so this is the D prime. So how accurate you are in making the change detection. So predicting when there was change, and you see when for two items that are metrically close, you have a higher precision of detecting change than for items that are far, and same for orientation. When the feature dimensions orientation, you also have better precision for close items than for far items. Not sure that it's a little bit complicated perhaps to follow all of this in a first lecture, but that was in the literature one effect that was clearly surprising, and we put on the landscape by accounting for it through DFT. Another source of evidence for this picture comes from multi-object tracking. So famous paradigm, someone called Piaget has established this over many years and looked at many different variants of it. And it's interesting because it reflects that same magic number 4, more or less, but it's in a very dynamic kind of situation. So for instance, in one version of this, you would see a number of items. They might be different in feature or not, depending on conditions. And for instance, one version, there is a frame where there is some perceptual cue as to which items you should pay attention to. For instance, these 4 items are highlighted, and it could be 1, 2, 3, 4, or 5, maybe items that are highlighted. And then when they, after some time, maybe 1 second, the highlighting goes away and the items begin to move around. For instance, you might be instructed to fixate all the time here in the middle, so you can't trace them with your naked eye, but that actually doesn't necessarily help you. And then at some point they stop, and one of those items, for instance, might be highlighted again. You have to say, was this one of the ones that were initially highlighted or not? That's the question you have to answer. Or you might be asked to actually point out which of the items were the original ones. So this probes whether you're able to sort of follow in time where these 4 perceptually now no longer discriminable items are. The other versions, for instance, where the items have different colors, and you have to say in the end where the but while they are moving, the colors are extinguished. They're all just gray, and then you have to reassign the colors to the items in the new location. So it looks whether you can sort of take along the memory about the color as they move around. And generally, the result of these kind of studies is that you are able to do this multi-object tracking up to 4 items, more or less. So, for instance, here, this actually varies speed. Yeah, but I don't think I have a correct, but that's sort of the literature that you can do that. So in our thinking, this work John Spencer did, in our thinking, this manipulation of pointing out the items would be one that modulates the input so that you're creating sustained peaks only at the locations that are cued, like these 6 locations here, 6 peaks with their corresponding inhibitory traces. So these would be self-stabilized peaks, while the other are sub-threshold inputs. And because they're self-sustained or stable, then when you start to move around these items, these peaks can stay, and they are tracking input, because even you have partial input, there's still enough to move those peaks around. If you move the input very fast, you can lose these peaks, because as you experience yourself, there's only a limited range over which you can actually track input in these fields. And what could happen is that you lose a peak just because it decays. You could lose a peak because it moves away too fast, or you could hypothetically, by fluctuation, a new peak could arise and then suppress an old peak. And so this is one of those studies from Corneri, who varied the speed with which these items move around. And this is the experiment here, and I don't remember how many items it was that people had to track. And the model sort of roughly captures the speed dependence, for instance. And there are other things that John Spencer modeled about that. So that's a phenomenon of working memory. There's much more to be said about that. Working memory, there's something about resources for working memory. You can sort of make an effort to keep something in working memory versus not make an effort, and you can actually selectively pay more attention to some items than to others in working memory and sort of allocate different resources. That's a way of speaking. Turns out that that is totally compatible with dynamic field theory. If you think of the resources as being some form of boost to the resting level, that is, if you have certain regions in the field where you boost the resting level, then any item in that region will be sustained more likely than somewhere else, and that's how you can account for effects like that. So the last thing I want to do is combine all of this, and this was one of our original models of DFT that is in the book chapter that I will be sharing. No, that's in the book chapter you already read. It contains all these instabilities and the memory trace, the NLP paradigm. That's a really fun paradigm. It's a developmental paradigm. We came, made a lot of progress with this on infants, and infants are wonderful because they will make coherent behavior without any interference by some cognitive interpretation of the task. So it's beautiful. If you get something working with infants, then you know you've really tapped into something deep and real. So the classical version of this paradigm involves a hidden object, a toy. Piaget, as some of you might know, was a philosopher, epistemologist who did some kind of armchair experiments with his own kids, apparently. He has a lot of influence on developmental psychology, even though he himself was just a philosopher. He never really did a controlled experiment. And who knows exactly what he did originally, but some of his experimental ideas have become major paradigms in development. Problem is always to find experiments that work. You're not giving kids instructions. You have to do something they like to do and reproduce behavior. And if you have found such a paradigm, it is often used extensively as an entry point into understanding cognition. So this initially was thought to be an experiment on this notion of out of sight, out of mind. It turns out that it's not quite the correct metaphor, but it is certainly a very interesting paradigm. So let me first explain the paradigm. This is my drawing of an infant seen from the top, right? The two eyes sound a little bit crude. And so in the original version, you have something that's attractive, a toy, maybe like a doll, and that you make sure the infant pays attention. You wave there, look here, there's a funny toy. And then you have a little box with 2 troughs in that box. One is called the A trough and the other the B trough. And in front of the kid's eyes, you hide the toy in one trough. So in one version, is a trough, and you put it in, and a lid, you cover that so the kid can't see the toy anymore. Or there could be a little piece of cloth over that. And then you it is also, I should say, you do that when this is out of reach of the infant. They can't get there. They might try, but usually they don't. And then you impose a delay that sort of the order of seconds, like up to 10 seconds maybe. And in some experiments, you vary that delay. And then you push the box into the reaching space, and the kids tend to be quite eager to get the toy, and they reach for the location where the toy is hidden, with a certain probability, and maybe even get the toy. There are variants with respect to that. I'll tell you one in a moment. These are called the A trials, and of course, experimentally, you make sure that the A trials are sometimes with A on the left, and in other kids, it's with A on the right. Ideally, you do this experiment only once, the whole sequence of trials only once on every baby, because they could actually be influenced next time from the previous experience. There's some evidence for that. So you repeat these A trials a couple of times. Conventionally, it's 6 times. Each time you have to wrestle the toy out of the hand of the kid and get the kid to tolerate that and push the box back and all that, and we start. And then you switch. So on the 6th or on the 7th B trial, let's say, you're hiding the toy under the B lid, in plain sight of the infant. Impose the delay, and they go to the A lid. That's the A not B era. Or it's called perseveration, because they do the same action again they did previously. They have a habit of, even though you would say there is some perceptual evidence that they shouldn't and should go to the other lid. So you can see why people say maybe out of sight, out of mind. It's not quite right, because they do reach for the correct location here. So it's not out of mind, right? They do know there was something attractive here about that. They are unable to update that in some sense. It's more like a lack of flexibility. That once they've learned it's at A, it's harder for them to switch to on a single try to B. It's really related to this delay. So if you make this delay short, they don't make the mistake. So there's a whole bunch of experiments that vary the delay, and then you can find a transition delay where they start to make the error. You can actually do that again across infants, because for a single infant you can vary the delay without some other problems. And so we know that the delay is important. And a couple of other factors that I want to skip over. Now, there is also, the toy doesn't play a role, but it's not the only thing. There is a so-called toyless version of this experiment that was made popular by Linda Smith and Esther Thielen and others. Here's an example. It's one of the Esther Thielen's collaborators with her son. And you see here, this is a box, and these are 2 lids, but there is actually no troughs on this box, and there are no objects hidden. So it's actually just the lids that you have. And there you see it's a selection task. It's a motor selection task. So in this version, all you do is you attract the attention of the kid to one of those lids. You do that, like taking up and saying, look, just wave that, and you bang the lid maybe on the table, then put it down, and then you impose the delay, shift it, the infant will follow the cue. No, not every trial, maybe 80% of the trials or 80% of the babies will follow the cue and pick up the lid that you first pointed out to them. And then if you repeat that a couple of times on A, then you switch and show them the B lid, show that in the same way, put that down, and then they make the persevetive reach to A. So the toy isn't actually essential. There's some debates about that in the sense quantitatively the effect is stronger if there's a toy, which we can actually explain in the meantime, but it's not essential. So how do we understand that? So we made a model that goes back to 2001 that really sort of put this dynamic field thinking onto the map. And so what we postulated was that at some point, the motor decision is driven by a field that is over some relevant movement dimension, could be space really, where a peak over the A location would motivate moving to the A location, a peak over the B location would do the same for the B location. And we varied whether the peak is stable or not, or how stable it is, as a question of development. That's where these parameter sets for different stages of development come in. And we postulated that there would be different sources of input to where these peaks are. So for instance, the waving action of the toy or of that lid would be specific input, in the sense it would be localized only around one of those locations, and it would be only present in time at that interval when you actually do that. The task input, as we called it back then, would be the perceptual structure. That is, you see there are two lids. Now, the infants are not actually reaching for the middle between these two locations. We get to that later. We have a version where they can do that. But in this case, of course, they will get for one of the lids. So there must be some input that specifies where the lids are. That's the task input. And then the Preshape input would be the assumption that the previous A trials matter, that during the A trials, you build up some memory trace of where you reach to, and that memory trace pre-shapes the field when you're next, showing the specific input and then ultimately putting the box in reaching space. Our first model actually has a conceptual mistake, I believe, which nobody seems to have noticed. When we published our correction, we had a hard time convincing people that that was really necessary, but we think it is. And the conceptual mistake was that we did not actually say that when the delay is over and infants can reach, that then a stable state must be present so that they can continuously couple their reaching movement machine to that input. And Vedina Dineva corrected that in her thesis by postulating that when the input, then when the system is, the box is shifted into reaching space, that will be a boost to the field, so that even if previously it had no peak, at that point it would create a peak from whatever subthreshold inputs it has. It's also an input, huh? It's a homogeneous input. So these are 4 sources of input rather than 3. And so the rough story of how this accounts for the effects. So if you, when you wave the lid or you show the toy, that will be localized input, and that would create a peak that will be essentially an input-driven detection decision, localized input-driven detection decision that also makes effectively a selection, because you're making one peak, not the other one a peak. Even though there is a little task input here, you don't generate a peak there. And while you do that, you might be laying down a memory trace, which would make it easier to induce the same peak again. And then there would be boost-driven detection when you put it into the reaching space, and that could induce a peak, or if there was already a peak, it would just stabilize that peak. And finally, there would be a difference between young and old infants, that young infants we postulated are below the memory instabilities. That is, when the localized input is removed, like the lid is being put down, then for the young infants, we said that there's no sustained activations or peaks for decay, and for older infants, there can be sustained activation. And so here the boost would then be critical, because if you had no peak after the delay for young infants, you would need to create a peak out of the subthreshold distribution, and that is what the boost would do. And so if there's a memory trace at A, it would be more likely that you're creating a peak at the A location than at the B location. And so that explains the A not B mistakes, because what happens in the young infants is that after a couple of A trials, when the boost comes, there is more activation at A than at B because of this memory trace at A. And so they would be making the peak there because the peak that was induced by the stimulus at B has decayed during the delay. While the older infants can sustain a peak at A, and therefore when the boost comes, nothing changes, and they will reach for the location that they had that peak at. Good. And yeah, so that's how the old infants would react to that. So here's a series of experiments, like simulation experiments that explain these data. So these are is an experiment with 6 A trials and 2 B trials. It's just time running, and you see here the temporal structure of this. This is the activation field. That's the memory trace. You see this is space this will be where A and where B locations are. And so, for instance, here, the A1 trial, this is where the Q would come. You would have localized input at A1 briefly, impose a delay, and then this ridge is the pushing into the reaching space that gives you a boost. And as a result, as you see here, the field forms a peak at the A location, and that suprathreshold peak will actually make a contribution to the memory trace. So between, you see, everywhere else the field is suppressed. So after this peak has been made, a new trial is started, and that's not modeled really here. You're just resetting the field to resting state, assuming that you've taken the lid out of the baby's hand and restarted the trial. So that's not really accounted for. See the next A trial, same thing. The memory trace grows. Third trial, fourth trial, fifth trial, and by this time you have a nice memory trace here at A. And so the B trial, the first B trial is here, this trial where there is a Q now to B, but then when you boost the field, you see the peak forms at A. It forms at A, essentially you see that the input has already decayed in this time interval. And so this smaller activation difference here at the B location than at the A location from the memory trace, and therefore you're responding to A, and that's done a second time here. If you had zero delay, that would not happen. You can see if you follow the boost right after this input, then you would be having more activation here. You would follow the cue correctly. So that's roughly how the model explains data, and there's a whole set of manipulations that were done in the literature that we did with the model that can be understood. For instance, you can make the two lids asymmetrical. You can have lids that when you lift them up, there is some exciting stuff there or not, and that can be the same on both sides, or it can be different. And all of these different kinds of effects were explained by the theory, by the balance of these different kinds of inputs, leading them to outcomes like that. So one aspect I want to point out here is sort of a critical aspect for our way of thinking. And this was a prediction that Evelina Dineva did, and actually we have a later paper where we did that stochastically. And it's around the problem of spontaneous errors. So here's an example from the simulation. You have all the A trials you see here, it's all A trials. And here's an A trial that is you're putting in an activation at A, but the peak forms at B. And that can happen in the model due to noise. You have fluctuations, and you remember the boost actually pushes the system through the instability, and that's where it's very sensitive to noise. And so in the model, you sometimes can get that. And then the model is reaching for B, but it also is laying down a memory trace at B, right? Because remember, it's the suprathreshold peak that lays down a memory trace. And then on the next trial, it does the same again. Actually, this is now already biased because influenced because there is this interference that I mentioned earlier that now the memory trace at B will promote selecting B, and the memory trace at A will have decay through competitive decay, which I pointed out earlier on, that when activation goes up at one place, it goes down at the other place. And therefore, there's a prediction here that the spontaneous error will have a tendency to repeat itself. And you're going to reach correct on B, because when on a B trial, now you induce activation here, the boost will more likely lead to a peak at B based on the memory trace, because the memory trace has been changed now. Now perseveration will imply reaching correctly on B. And that is actually what is observed for kids. So I actually didn't put that slide in, but that's a experimental result that people have found, that kids who do spontaneous errors will tend to reach correctly on B. And we made one sort of non-trivial prediction that I already hinted at, that we also predict that spontaneous errors will tend to repeat themselves. So here is the probability of making a spontaneous error the first time on different trials for the model and the infants. And you see here an increase up to 4 and then a plateau. And that comes from a subtle effect that I didn't explain, that in many of these experiments, there's a so-called training regime where initially you make it easier to reach to A by, for instance, putting the lid closer to the infant on the A trial. And it's kind of funny. And with the toy, for instance, you make the toy somewhat visible, not completely hidden. And it's also interesting why people do that, but that's certainly routinely done. And the infant data here from Estefani's lab were of that nature. And that makes that the spontaneous error is more likely to occur on the later trials when the two locations are more symmetrical. Initially, there's a bias toward A. And that bias itself might actually explain some of the perseveration. So that's why there is this trend here. The significant thing here, though, is the repeated error. So you see, just in terms of number, the probability of making the mistake again is much higher than the probability of making that mistake the first time. On different trials, from different, in the model, from different trials, different random seed, and in infants, it's a different infant. More than twice as likely to make the error again. And there are other kind of conditional probabilities that we can make to corroborate that. There's some technical reason why that's important, because you could think, well, the infants make the mistake because, like, some infants tend to the right, some infants tend to the left, and so if they tend to the left, that persists, and they always go to the left. And you can compute from the model that leads to a different time course. Then the probability here has a different slope, and that can be excluded from this. But the other important idea is that this is an effect where you see that previous reaches matter, that they leave a trace. And why do they leave a trace? Well, because there's a suprathreshold peak which has been amplified, not small, just a small difference, has been amplified into macroscopic difference. And remember that in the field, that means that we really make a selection decision, a commitment to creating a peak that suppresses the alternatives. And that macro state now leads to a macroscopic difference in memory trace, really laying down a memory trace here and not there. Remember, this other procedure would be to just look at any moment in time where the maximal activation in the field is, like a readout process for that, which some of the connectionist models that were postulated here in this context have used as their readout procedure. Then there is nothing about the readout that would make any difference between having read out this location versus that location on different trials, different moments in time, right? That does not lead to a difference in memory trace, because the state of the field is not macroscopically different. So it's really quite important to have that notion. So this will be direct empirical evidence that a decision leads to a macroscopic difference that's large enough to leave a different memory trace, or actually vice versa, that a large enough difference in activation leaving a memory trace is a decision. That's what would be perhaps the correct way to look at that. So I realized that this was a somewhat more difficult lecture. If you look at the background reading, this one is covered in part by the chapter that you did study. I instructed you when you did that exercise not necessary to read the second part. You can now maybe read the second part that contains an analysis of the NLP. You will also see in that chapter that we discuss what we call the sandbox version of the NLP. That is a case where there are no lids, where you actually hide a toy in the sand, and then you find that kids are not categorically wrong, but they're metrically attracted to the A location. Very interesting perspective. Out of which comes the spatial memory, the spatial position hypothesis. But other aspects like the change detection aspect and the capacity of working memory and so on are not discussed in the basic chapter. There are in the book more advanced chapters. I wasn't going to ask you to read those, as those are make a lot more assumptions about other things that you need to know. For those who are interested in that, I'll be happy to make those chapters available to you. So in summary, I don't even need to take you through this. So that sort of covers now the complete set of dynamical states that we found important in the basic mathematics of the dynamical field. So we talked about detection, selection, and memory. Those are the three functions with which we do everything else. So in the new year, you will have a couple of lectures where we'll go to higher cognitive things like the grounding of spatial concepts and movement concepts and language and sequence generation and serial order and so on. And all of that will just play with these three fundamental stable states and their instabilities. They can do all that. I would say actually we can reach pretty much all of cognition just through those elementary neurodynamic functions.